Okay, so now let's take a look at what happens when we specify different priors in the model that we are looking at, this simple model of reaction times, right? So as I mentioned in the last lecture, there's a range of priors that you can choose. You can choose a different set of priors for all the parameters. Here I'm just showing you some possibilities for the mu parameter. So what we're going to do for the mu parameter, and so what we're going to do is that we will change in the BRM function. Remember that in the BRM function there was a parameter for priors, right? There was a list that you could specify to decide on what the priors are for each of your parameters. We will simply keep changing these priors in the model, and we will look at the posterior distributions of the mu and sigma parameters as a function of these different prior specifications. So this approach of looking at the posterior, how the posterior changes as a function of the priors, is called a sensitivity analysis. Okay, so I'm just giving you an example of that. And the reason we are doing this sensitivity analysis is that our first prior specification was not very satisfactory. Why? Because the prior predictive distribution was largely nonsensical. Right? So that means that the model itself is not a great model of reaction times. So we're going to try to think about some better models. Okay? So one possibility would be to go even more extreme in terms of uninformative priors and have this kind of uniform prior, which I discussed earlier, this uninformative prior, and we could study the consequences of that. Right? There's no harm in deciding on a very vague prior to see what happens to the posterior distribution. So let's compare what happens. This is the original model that we had fit I'm just showing you the mu parameters, okay, just to illustrate the point. This is the original model that I had fit with the uniform priors with 0 and what was it, 60,000 for the mu parameter. And now I'm using these ridiculously uninformative flat priors that I just fit. This one here, right, is a completely insane prior in the sense that it even allows impossible negative values, right? So, but what you'll notice is that the data, I have so much data from this one subject that the posterior distributions are pretty similar. They're pretty unaffected by the prior specification. So what this sensitivity analysis is showing is that the posterior is largely unaffected by the prior specification. We can check this even further. So let's go to the other extreme and choose a relatively informative prior. So now I've chosen a prior with a mean of 400, standard deviation of 10, which is very, very tight. Okay, this is a very strong prior belief that the value is the reading times are ranging from 100 plus minus 20 milliseconds, right, with 95% probability. So that's a very informative prior. So let's see if the posterior changes now for mu as a result of this informative prior, right? As I mentioned earlier, some lectures ago, the posterior is going to be a compromise between the prior and the likelihood, but if you have a lot of data, the posterior will be pretty much affected by the likelihood. So you'll get exactly the same result as a maximum likelihood estimate, right, for the mean of the posterior. So let's look at this again. Here's my original model with the uniform priors that I fit earlier in the previous lecture. Here is my flat uninformative priors. As I showed you, I have very similar estimates here. And now I have an informative prior. And if you notice, there's a slight shift in the distribution to the right, okay? Because I had 166, 171 as the 95% credible interval. Now I have 170 and 175, right? That shift to the right happened because of the tightly informative prior pushing the posterior a bit towards it, But because we have enough data, I did not push it much, right? So we still have a lot of data, and that means that the posterior is going to be largely influenced by the likelihood specification. Okay? Well, let's try another example. Like we could use what I would call a principal prior under our terminology. This is a prior which assumes a reasonable mean, but allows a lot more variation, okay, in the mean, right, as a prior, okay, for the mu parameter. And again, what I notice is I'm just showing you all the fits now. Okay, this was the original fit. This was the fit with the uninformative flat prior. Here's the fit for the intercept parameter and the mu parameter with the informative prior, and finally the principal prior, right? So let's compare what happens between the informative and the principal prior. So as I showed you in the previous slide, with the informative prior, I get a slight shift to the right towards the informative prior when I look at the posterior distribution credible interval here. Now, if I make the prior much more uncertain by increasing the standard deviation from 20 to 100, as I just did here, notice this here. I've got 200 mean and standard deviation 100. Earlier I had 400 mean and a standard deviation of 10. That is the informative prior, and this is a principal prior in the sense that it sets a principal mean for the mu parameter but allows a lot of uncertainty, right? What this is expressing, this parameter for mu, this prior for mu is expressing is that I think that the prior mean is about 200, but I'm not very sure about that, okay? So what we notice now when I have this kind of principal prior is that the posterior now looks a lot more like the posterior that I had with the uninformative and the uniform priors earlier, right? So the effect of the prior has weakened because of the large standard deviation in the principal prior. So this, what I'm showing you right now, this is exactly what I would report, in a paper if I were reporting a sensitivity analysis. So sometimes I do that just to demonstrate how much the posterior distribution changes as a result of different prior specifications, right? And you can imagine why this is so useful as a data analysis strategy. I could now fit different models with priors that reflect different prior beliefs, right? So suppose I'm engaged in a scientific argument with an opponent in the field. By opponent, I mean a scientific opponent, so not a personal enemy or something like that. So in that situation, my opponent might have an alternative prior belief about the problem that I'm studying. So what I can do is, given my data, I can say, okay, let's take your prior belief and plug it into the model and see what the posterior gives us. So what we can do is we can learn we can figure out what we can learn from the data given alternative prior beliefs, right? That's what this sensitivity analysis is doing. The vague priors are expressing the prior assumption that we know nothing about this parameter or very little about this parameter. The informative priors are saying that we know quite a lot already, right? So we can bring that information into the game. So this is why the Bayesian approach, this is one reason why the Bayesian approach is so useful. It allows you to think about what you already know and to interpret the data in the light of alternative prior beliefs, right? That's the application of a sensitivity analysis in real life data analyses. Okay, so but what we found in this example is that the sensitivity analysis shows that the posterior is not affected much by the prior specification, right? So you can't get overexcited about the fact that there's a 4 millisecond slowdown here, a shift of 4 milliseconds to the right is not really meaningful in terms of, changing the meaning of the posterior distribution really. So in that sense, it doesn't really affect the posterior, right? And this should remind you again, of the discussion we had earlier with the analytical base that we did with the conjugate cases, that the posterior is a compromise between the prior and the likelihood. So I have already harped on this point quite a bit, so I won't go on about this. But I just want you to keep that in mind, that we are really talking about what we have learned from the data in the light of our prior knowledge or beliefs or assumptions. Okay. So in general, I would suggest that you carry out such a sensitivity analysis. I often don't report it in the final published paper, but I will certainly do it in my own analyses, which I generally put up on the internet after I publish the paper so people can see my analyses. But what will happen with you, if you're analyzing lots and lots of data with a Bayesian framework, after a while, when you're working on a particular problem, you will have a very good sense of whether the posterior is going to be sensitive to prior specifications or not, right? So often, with lots of experience, you won't even need to do a sensitivity analysis because you know what's going to happen, right? The posterior won't be affected much. And so this is, however, in general, when you're working on a new problem, you should think about a sensitivity analysis to understand what's happening in the light of prior specifications. All right, so one thing you can do now is to fool around with this model a little bit, change the priors, try some other priors, right? If you look up the STAN manual, you will see lots of possibilities that you can choose, right? And then what you can do, we provide the code in the textbook, so you can look at that later. You can produce prior predictive distributions with each prior specification. I showed you one example of a prior predictive distribution, but you can generate a prior predictive distribution with any set of priors. And then look to see, your goal should be to check whether the prior predictive distributions are reasonable given your intuitive beliefs about what you think the data should look like. Reaction time data should have certain properties that would make sense even before you've seen any data. So you could look at the prior predictive distributions to diagnose the model before you've even seen any data. Okay, so you should of course read the textbook chapter 3 to get an idea of all the details that I have skipped. There's a few little details about prior predictive distributions and so on that you should know about. And so what we are going to do next in the next lecture is we're going to look at what kind of data the model is going to generate once we have incorporated the information from the existing data. So we're going to look at future data from the model to evaluate the plausibility of this model given the data that we have. That's the next lecture.